Hello, Math 125 students. Welcome to the lesson about log equations and applications.
Do you remember from the previous video, we actually talked about log base b to the x. They cancel with each other, so the answer is just x over here. If you have the same base b to the log bx, then also they cancel with each other, so it becomes x. So we have already studied in the previous video about this. So as an example, look at this. If you have log base 7, because their bases are the same, the answer is just x because it looks like it's gonna cancel and cancel the 7s with log. So the x is the only answer. Another one is if you have 7 to the power of log base 7x, then you can also cancel the same base with log. So the answer is basically x as well. Okay, I'm going to introduce you new laws of logarithm. The first one is called power law. It looks like this. Log base b x to the power of some power. You can bring this exponent n to the front. N times log base bx. So look at this example. If you have log base 2x squared, you can bring this exponent down to the front and make it as a multiplication. 2 times log base 2x, like so. This is the first beautiful law that you'll be studying today. Another one is something called product law. In other words, if you have something multiplied with another thing, like x and y, you can split this into two different logarithms like this. Log base bx plus log base by. You can split this into two different log, but be careful, it has to be plus sign. For instance, let's say you have log base e3 plus log base e5. You can combine them as a single logarithm by using the product law. It's log base e, this number, times by this number. So 3 times by 5. Similarly, if you have log base bx over y, it's called quotient rule because x over y is some sort of division thing going on. So it's we have a quotient. Log base bx over y equals log base bx minus log base by. You can split this one single logarithm into two different logarithms like this, but be careful, it has to be a minus sign. As an example, log of something, say 15 minus log of 4, for example, then using the quotient law, this two different logarithm can be written as a single log, but it's a fraction. So log of 15 divided by 4, something like this. You can combine two different logarithm into one. The last law that we're going to study today is very useful. It's called change of base. And let's suppose you have log base ba. You can make it into two different logarithm as a fraction. Please note, a goes to the numerator, and then the base b goes to the denominator. So log base ba can be written as log of a, which is on the numerator, with any base that works, divided by log of that same base, b. We put the b as a denominator because b is at the bottom of a. The example we have is log of 7/10, for example. If you want to write this as a fraction, you can write it like this fraction. And then the hidden base is 10. So you have successfully changed the base from 7 to base 10 here, base 10 here. You're welcome to change the base to e, then something like this. Or log base e10 is equivalent to the natural log ln. So did you notice that this expression is equal to this one is equal to this one is equal to this one? So you are free to choose any base that you like to use. as long as the base is valid. Okay, so that's enough for the first page. Question number 1. Use product law or quotient law to condense the following. Condense the following means you combine the two different logarithms into one. I see there's a minus sign going on. If we have a minus sign, we can combine them as a single logarithm using quotient rule. See, 12 divided by 3 using the quotient rule, this rule over here. Then it works out to be 12 divided by 3 is 4, so we have log base 2, 4. And then did you notice that 4 can be rewritten as 2 to the power of 2? Like this. And then log base 2 and 2 cancel with each other by identity number 1 or cancellation law from previous video. Move on to the next one. I think by now you can do this by yourself. We have a plus sign, that means we have to use the product law. Let's leave it like that. Part A. Condense the following. Log 69 plus log 68 minus log 62. We have now 3 terms here. First, we're going to use the product law to combine the two things into one. But did you notice that 9 times by 8 is 72? And then log base 6, 72 minus 2 means division using quotient law. But 72 divided by 2 is 36. Everyone, 36 is what? 6 to the power of 2. Again, using the canceling law, the answer is 2. Let's solve this expression here. Log 8 minus log 2 over 5. You can use the division using quotient law. But 8 divided by 2 over 5 is equal to 8 times by 5 is 40. Like this. But 40 divided by 2 is what? 20. Like this. And then finally, log 20 plus log 5. Using the product law, 20 times by 5 becomes 100. And then there's a hidden number 10, you know that. And 100 here is same as 10 to the power of 2, so you can replace. Good news is that you can cancel this log base 10 and then this base 10. So what's the answer again? The answer here is again 2. Thank you very much. That's the end of the examples for the second page. Let's move on to the next page. This time, everyone, we're going to expand a logarithmic expression. This is kind of condensed logarithmic expression, and now we're going to expand it. It's kind of opposite of what we've done before. Currently, we have multiplication sign going on. Multiplication sign means we can use the product law to make it plus sign. And then there's another multiplication sign here, 7 and 2. So 7 times by x, you can split into 2 different log. And then 2 times y, you can also split into 2 different logarithm expressions. This expression just came from this expression. And this expression came from this expression. So that's the answer. Let's do part B. Currently, we have division sign here. So division sign or fraction means we have to use a quotient rule. So it looks like this. From the previous video, any logarithmic expression containing 1 is equal to 0. I hope you remember that from previous video. So this whole thing is 0. Finally, we can bring the k down to the front using the power law. And congratulations, this is the answer for part B. Lastly, let's do part C. Did you notice that if we have a square root expression, you can change it to the power of 1/2. And then good news is that you can bring this power to the front. And did you notice that we have log of x cubed multiplied by y to the power of -4. This multiplication sign means we can use the plus sign using the product rule. Did you notice that I have a huge bracket after 1/2 because this 1/2 must contain this whole thing. So please don't forget about the bracket. Using the power rule, you can bring 3 to the front, you can bring -4 to the front. And congratulations, this is the fully expanded form. And that's the end of this slide. Let's practice more of condensing logarithmic expressions. The first one should be straightforward. Second one and third one probably be harder than the first one. Okay, let's try the first one. Using the product law, you can multiply this one and this one together into a single logarithm. Then 2 and 3 multiply together to become 6. And then x4, x5 multiply together to become x9. And that's the answer. Second question. Before we actually condense this expanded form, you can probably bring this 1/2 and 3 at the top of y and z as an exponent. The reason is we are using both of them as power rules. Right? Did you notice that this power 1/2 is the same as square root? So if you really want, you can change this to like this. Now we are ready to condense this. Did you notice that we used the quotient rule or quotient law to combine two different log into one like this? Now the next one is we have plus sign. This plus sign means you multiply this with this fraction. So the answer is x times z cubed divided by square root of y. Congratulations, that's the answer for part B. Last question for this page. For this last expression, take a look at this standard term and then the last term here. Log base 7a divided by 3, it's equivalent to saying that 1/3 times by log base 7a, 1/3 times by log base 7b, okay? Then, do you remember what we did before? We brought this power or this coefficient as a power, brought this coefficient as an exponent. We're gonna do exactly the same thing for this guy. But from earlier mathematics courses you've probably taken before, a to the power of 1/3 is the same as cube root of a. B to the power of 1/3 is the same as cube root of b. And then combine all together, we get this is our final answer. Or you can probably combine them together if you wish. Okay, move on to the last page. Okay, here's the last example for today. Please note there's a typo in here. Log base 511 equals b. So if I rewrite this, yes, this must be the correct form. I forgot to put equals b in here. Use the change of base formula. If you don't remember what that is, please go back to the beginning of this video and review this formula again. And laws of logarithms to rewrite each expression in terms of a and b. Let's try the first question. We have log base 11.5. Using the change of base formula, okay, now we're living in a free country and you can choose whatever base you like. But because we have base 5 here, base 5 here, maybe we will be clever if we choose 5 to be here and here as well. So, like this. Then we have a good news. Using the cancellation law, log base 5, they cancel with each other. So the answer here becomes 1. The reason why it's 1 is because it's same as what? 5 to the power of 1. So if you cancel this and this together, then the numerator is basically 1. And then the denominator is also good news because log base 511 is equal to b. We have successfully answered this in terms of a or b, or a and b. Last question. Using the quotient law, we have obtained log base 11.6 minus log base 11.11. Oh, this one is good news. They cancel with each other, so the answer here is just 1. So changing this to 1 is easy. How about this one? To answer this question, we need to change this base in terms of base 5. Here, like we did before in the previous question, we're gonna choose base 5. Then the good news is that the numerator log base 5.6 is exactly the same as a, and then log base 5.11 over here is exactly the same as b. So the answer is basically a over b minus 1. And we have successfully changed this log expression in terms of a and b. Thank you very much. That's the end of the video. This is the last lesson on exponential and logarithmic functions. In particular, we're going to study exponential and logarithmic equations in section 4.6. Part number 1, exponential equations. As a warm-up, let's find the common base for 4 and 8. The common base for 4 and 8 is 2, because 2 to the power of 2 is 4, and then 8 can be written as 2 to the power of 3. Did you notice that we have the common base for these two numbers? Let's try this one. The common base for 25 and 125 is 5. 25 is 5 times by 5. 125 is 5 times 5 times 5. Therefore, the common base is obviously 5. If you understood this warm-up, I think we are ready to tackle these questions. Solve this equation by finding a common base. As you know, 125 can be written as 5 to the power of 3. And then 25 can be written as 5 to the power of 2. If you have this kind of expression here, you can multiply this exponent with this exponent together. As soon as you have the same base, you can ignore this and then write down the exponent. This exponent equals this exponent. The answer is x equal to 2. Let's try the similar process for part B. In this case here, you need to change 1 over 9 in terms of base 3. I hope you realize that 3 times 3 is 9. Therefore, 3 to the power of negative 2 is same as 1 over 9. Using the similar rule here, you can multiply negative 2 and x minus 3 together. So we get this. This means x is also equal to 2. This is the end of this example. I want to say something before we move on. Solving an exponential equation is easy if you can find the common base like this. 3 here, 3 here, 5 here, 5 here. It's really easy. However, consider the next page. Look at this. 8 to the power of x equals 23. What is the common base? Well, the answer is there's no common base. We need to use another method to solve this kind of equation, and the answer is use logarithms. For instance, apply log both sides. That's step number one. The beautifulness of logarithm is that you can use this law. You see that you can bring the exponent to the front. And then what do you do next? Because you're solving for the x, you divide both sides by log of 8. To evaluate this x, which is log 23 divided by log of 8, you just use your calculator. The answer is 1.6 blah blah blah. So maybe 1.602 might be a good one. Thank you. Let's move on to the little bit harder example. Solve the equation e to the 2x minus e to the x equals 56. To solve this equation, I'm going to move 56 to the other side. And I'm going to change this a little bit. Did you notice that we have 2 times by x? This is equivalent to like this. And I see some good news here. E to the x, e to the x, they're the same expression. Isn't this look like something square minus something minus 56? Oh, then it's like a quadratic equation. Assuming that you're setting a to be e to the x. Then you can write this equation looks like this, which is a quadratic equation, and it looks much better. And how do we factor this? Well, I'm going to assume you know how to factor. Well, two numbers multiply together to become 56, which is 7 and 8. A plus 7 times a minus 8 equal to 0. This is the factor form of this trinomial. Everyone, we have two cases. Either a plus 7 is 0 or a minus 8 is 0. But a plus 7 is equal to 0 means because our a is equal to e to the x, we can rewrite this equation as we currently have two situations. E to the x equals negative 7 or e to the x equals positive 8. Do you remember? If we have this kind of situation going on, we put log on both sides. We're going to do exactly the same thing. Hang on one second. I have one question for you. Are you allowed to have negative number inside the bracket here? If you said no, then you're correct. You're not allowed to have negative or even 0 as an input for the logarithm function. So, this equation does not have a solution. Let's write it down. Because log negative 7 is undefined, then the only equation that we have to worry about is this guy, e to the x equals positive 8. We are going to put the log on both sides. However, let me tell you something. Whenever you see e, like over here e, I think I should have used ln, which is natural log. Natural log and e closely related to each other. You must use ln when that happens. In this case, I prefer to put ln on both sides instead of log. This time, ln of 8 is positive number, which is totally fine. So it works. You can bring the power down. What's ln of e? Do you remember the cancellation law from previous video? Log base e is 1. But I can check with you. Ln of e is 1. That's a good news. X times by 1 is just x. Using our calculator, ln of 8 is basically this, 2.079. That's the end of the first part of the video. Thank you very much. Part number 2. We're going to solve logarithmic equations. We're going to start with the very simple logarithmic equations like this. Solve log base 8 x plus 6 equals log base 8 4 minus x. Whenever you see this type of question, I hope you're happy because you can just cancel log 8 on both sides. Then we only have the following. We get the solution x equal to -1, but we do not yet know whether this is a correct solution or not. The reason is, are you allowed to have a negative number as an input for this log function? If you said no, then you're correct. You cannot have negative number here. You cannot have even 0 here. Only positive inputs are allowed. So we need to check the equation. Put -1 into the x here. Put -1 into this x and hope that you don't get 0 or negative as an input. -1 plus 6 is 5. So we're happy that this is a valid logarithmic expression so far. Check the right hand side. For take away -1 is also 5. This means, everyone, -1 is the correct solution because left hand side equals right hand side. Here's a warning though. Suppose you have log base bx, log base by, log base bz. You cannot, this is illegal. You cannot cancel one log on the left while you're having 2 logs on the right. You cannot do this. Please remember. The idea is that you must have only one log rhythmic expression on the left, only one log expression on the right. Then you can cancel these one at a time. Then it's allowed. But you cannot cancel this at the same time. Instead, you have to do this way. You see the plus sign here? You can maybe combine or condense this expression into one single logarithm like this. Log base b y times by z. Then you can cancel one log at the same time. Then it's correct. Okay? Let's try the next question. Here's the next example. Find the solutions of log x plus 3 equals 1. Whenever you see a pure number like this, here's my hot tip. Whenever you see a number, you look at what kind of base you have here. If there's no number here as a base, then the hidden number as a base is, the hidden number is 10. So the base number is 10 in this case. Okay, here's my hot tip. Whenever you see a pure number, you can change in terms of log of the base number. For example, something like this. Log base 10, 10, 1, you know. Then you can rewrite this whole equation as the following. This equation is equivalent to this equation. Now, do you remember you cannot cancel this. You're not ready to do this yet. You need to combine 2 different logarithms into one of them. Then you can cancel one at a time. Did you notice that? We use the product rule for logarithms to combine x and x plus 3 together. Now you're allowed to cancel like this. Then we get x squared plus 3x equals 10. Move this over to the other side, then you'll see something really nice. You can factor this quadratic expression and you get the solutions x equal to -5 and 2. Still, it doesn't mean we're done because we have to check whether these numbers are valid or not. To check this, plug this into the left-hand side and hope that you get the right-hand side. Oh my gosh, if you look at the left-hand side, when you plug it in -5, I get log of base 10 -5 right away. Are you allowed to have a negative number here as an input? If you said no, then you're correct. You're not allowed to have it. In other words, -5 must be rejected. Let's check the plug it in 2 into the original expression. Yay! We plugged 2 into the original left-hand side, which is log 2 plus log 5 equals log 10, which is equal to 1. That is the same as the right-hand side. Hence, 2 is the correct answer. Next example. Solve the equation 2 times natural log of x plus 3 equals 7. If you remember what I said as a hot tip from previous example, whenever you see a number, you can change to a logarithmic expression. But let's do it later, okay? The reason is your life will be much easier if you subtract both sides by 3. This looks much better, isn't it? Even if you want to make your life simpler, divide both sides by 2. And then, do you remember? ln of x is log base e x. So, if you want to change the pure number 2 in terms of logarithmic with the base, 2 is equal to log base e squared. It's equivalent to each other. So let's change this to. So far, we have natural log of x is equal to log base e squared. But do you remember from earlier? Log base e is the same as the natural log. Like so. I'm happy you're happy too because we can cancel one log at a time. Yay! We have just found out the answer, which is x equals e squared. If you check the left-hand side, you can bring the 2 to the front. So you get 2 times 2 natural log of e plus 3. But 2 times 2 is 4. But what is natural log of e, everyone? Natural log of e is 1. So 4 times by 1 plus 3 is 7, which is the right-hand side. Therefore, x equals e squared is the correct answer. Let's move on to the last example. Here's the last example, which is a word problem. If you have taken a chemistry class before, you probably heard of something called half-life. This problem is related to the half-life of this substance, uranium-235. The half-life of this substance is, wow, 703,800,000 years. Well, let's use the half-life information first. Whenever you talk about half-life, at least in this course, think about this formula from before. A equals A naught e to the kt. This is the final amount, initial amount, e to the power of relative growth rate k times by the number of years t. We know t to be 703,800,000 years. We don't know what k is yet, but we know half-life means A should be 1/2, A naught should be 1. Or you can think about A naught is 100%, A, which is the final amount, must be 50%. That's the meaning of half-life. So let's write it down. We need to find the unknown variable k, which is the relative growth rate. To find this k, we have to put law on both sides. And then the good news about ln is that you can, bring this exponent. You can bring this exponent to the front. And another good news is that ln of e is equal to 1. So to find k, you divide both sides by this number, 703,800,000. Once you have figured out the k value, then we are ready to tackle the actual question. How long will it take for 10% of this initial value to decay? 10% to decay means what's the final amount? The final amount is 90% leftover. So your final amount should be 900 grams. And you'd repeat the same process as before, put on both sides and isolate the t. It's kind of similar process. Before you do it, of course, don't forget about dividing this number, both sides. And then you can bring this exponent to the front. You know, kiss and flip means uh, you multiply this denominator to this guy divided by ln of 1/2 to isolate the time t. So that's what I've done here, kiss and flip. And take out your calculator. And enter everything you've seen here. And the answer is 106,979,777 years. Thank you very much. This is the end of all the exponential and logarithmic equations.